Okay, we are all set for the part two today. And yeah, let's go for the next type of insurance. And yeah, so I'll discuss the type first and then come back to here. I think, okay, I think I can use it. So I'll discuss it here. So next type is the level term life insurance. So in this case, so in the previous case, I mentioned that the insurer covers the benefit payment from the time of purchase to the uh, point of death, no matter how they have to wait, they will provide. So in this case, it is term life. That means we have the time of purchase and the TX start from 0, goes to somewhere, and after n years, the coverage ends and we only pay as the insurer. The benefit is paid if and only if the death occurs in between 0 and n. So that's the difference. That means if I get here, B is paid and from this point onwards, no benefit applied. So that's the case. So in the whole life case, the benefit is being paid from 0 to infinity, but in here we have the benefit payment period from 0 to n. After that, we don't pay anything. And here, so since we know the term n, so the net single premium is something manageable. So which is also the actual present value. And that means we know at most we have to wait until n years. So that means if I pay the benefit at the n year end, so that is the last time I have to pay the benefit. So if I can carry 100,000 throughout this time, so then I'm ready to pay a benefit payment whenever it is needed. If the benefit is not paid, so then I don't need any 100,000 for that. So this means the previous 100,000 is can be allocated to any other kind of business line or for a different portfolio. So in here, the death benefit is paid at the moment. That is why it's continuous, and that's why we use TX. And if the death occurs during the next n years, since it is level and we are going to talk about the net single premium, we let the benefit to $1 and TX is now less than or equal to n and 0 otherwise. And the discount factor is TX, but it's only valid for the given time. So that means now this is a function or step function where TX is less than n and 0 otherwise. And for benefit, 1 if TX is less than n, 0 if TX is greater than n. Then the present value random variable is VTX again, but the actual present value is denoted like this. Actual present value of a person who is at age X for the next n years, the coverage time, and it's only for the term. So that's why we put 1 over X and it is continuous. We use bar. So that is the actual present value of a $1 benefit payment, term life insurance, which is continuously considered, and the death benefit is paid at the moment of death and only valid for the next n years at from the purchase point onwards. And The only difference is for the integration, we goes from 0 to n, the same function, vtx times pxt times mu x plus t. And vtx, so vt is e to the power delta t, delta is the force of interest, and then fxt is given from here. So this is fxt, which is the usual definition we use in the second chapter. So that is the picture for this term life. And to get the variance, we need to have the second movement. And as we discussed, just replace delta by 2 delta for this net single premium or the actual present value of the term life insurance. And this will become 2xn, and it is term. So that is how the definition used. That means we have the actual present value of this term life insurance for n years, and 2 denotes it's the second movement. Now, if we have the first movement and the second movement, we can find the variance using this equation. So that's how we can find the variance for this present value random variable for a level benefit term life insurance of $1, and the term is n years. And now I mentioned for the term life, the benefit is paid if the death occurs in between 0 and n. Then we can define a different type, which is called the pure endowment, and it only gives you a survival benefit. That means if you purchase the insurance at age X, your TX becomes 0 at that point and it goes to N. And if the person survives from 0 to N, there's no death benefit, but there's a survival benefit. If that person survives to N, so there'll be benefit payment at age X plus N. That means during this time, pay nothing if death occurs. But if death occurs after n years, at age X plus N, there's a payment, and we don't know when the death occurs after that, but it is sufficient to know that the person has survived for n years. So that means the benefit payment is like this. The benefit function is 0 for Tx, which is less than or equal to n, and 1 for survivors greater than n. So this is the opposite of this level benefit function. And the present value, now you can see if there's no payment occurs between 0 and n, there's no any value to make it or bring back to present. So it's 0. But the payment is made at age X plus N or time Tx equal N. That means the payment occurs in this time and we have to bring it back to here. N is a fixed term, we know that. So the present value is v to the power N. And by multiplying this, so you will see that there's no payment for Tx less than or equal to N, and the payment only occurs at N. So the present value is v to the power N. That means the net single premium or the actual present value for this one is denoted by actual present value. Though it is continuous or discrete, there's only one point of time for the payment. So we don't need a bar to indicate it. Age is X, term is N. If that person survives up to N, the payment occurs. So that means, so in the term insurance, we put 1 over X. In the PO endowment, we use 1 or we put 1 over this term N. So since there's only one time of payment, the present value is just the Vn times the probability of surviving up to that. So this is the survival probability. And it is same as Pxn. So that's how we got this one. And it's only one point in the timeline. And to get the second movement, so now we have to replace in here the n in here should be replaced as 2n. So that means the second movement of the actuarial present value of the PO endowment term is V2n Pxn. So we only replace n in the present value random variable, not in the probability function. So you can derive the variance equation from here. So it is just changing the form. So for this one, it's Pxn. For this one also, it's minus En Pxn to the power 2. So we have a common factor, which is V2n. And for here, 1 Pxn and 1 minus Pxn, which is give V2n Pxn Qxn. That's how we get that variance. So it's easy. And it's kind of the variance term of the Bernoulli random variable. So in the Bernoulli random variable, we say if we get AB with probability of P and 1 minus P, the variance of X is this. So this is same as this. That means Z has a distribution of a Bernoulli random variable with the probability of Pxn, because 1 minus Pxn is Qxn. So that is also a derivative of this type of PO endowment. And now you might think, so in the level benefit term life insurance, we have a benefit payment in between 0 and 1. In the PO endowment, we have a benefit payment at the point of N. And there's no benefit payment in between 0 and 1. So what if I join these two products together? Term life plus the PO endowment. And that product is called the endowment insurance. That means from 0 to N, benefit paid if death occurs. And at this point, the benefit paid if survived. So that means suppose a person who is at age 25 purchase a 20-year term life insurance. So then if that person survives for 20 years, that means at the age 45, the survival benefit is paid. That is the pure endowment part. But if that person dies within the next 20 years, the benefit is paid at the moment of death. That means the benefit function is 1 if Tx is less than or equal to n, and one if Tx is greater than n. So that means throughout the entire future lifetime, benefit is 1. And for the present value, since we don't know the actual time of death in between 0 and n, so it is Vtx, but we know that the survival time point is n, and we don't want the actual death time beyond n. So then benefit is V, or the benefit is paid, and the present value of that benefit is Vn. So this is a summation of Bx's in term life and pure endowment, and the Z's of term life and pure endowment. That means you don't need to do integration here, just the actuarial present value, the net single premium of a continuous endowment insurance of n terms is the summation of the actuarial present value of a term life insurance of n years plus the actuarial present value of the pure endowment for n years. So that is the equation. Now you can see, if you know the present values for the term life and the pure endowment, you can find the endowment, or in the other ways. In the table, the actual, so we know that we have the standard life table. So in the standard life table, these two are given, which means the endowment insurance present value and the PO endowment part. That means if you want to calculate the term life insurance, just find these two values from the table and subtract it to get the term life insurance net single premium, or the actual present value. And like before, we just need to replace delta by 2 delta to get this second movement. And the more specifically, so 2 delta is only affecting the term life. And for this one, we saw that when it's become 2a, we just need to replace n by 2n. So two terms, which means both terms have their unique substitutions. First part needs delta, second part needs uh, n. So once you have the second movement, you can find the variance using those. So that is the benefit, level benefit endowment insurance. And now, so in these two cases, we had a term which is 0 to n. And in here, the benefit is paid between 0 and n. In here, the benefit is not paid between 0 and n, but at the moment of n. In here, it is a combination, but still the benefit is not being paid after n years. So that's why we use a deferred whole life insurance. That means you sell the policy at age X and pay nothing between 0 and n. And after that, benefit is paid at the moment of death. That means you are in age X, and from X to X plus N, you don't have any benefit payment. But after that, you have a benefit payment at the moment of death. So it's same as you are buying a life insurance after N years from now. So if you uh, think that the benefit, in terms of the benefit function, benefit is 0 for Tx is less than or equal to n, but 1 for Tx is greater than n. And benefit the present value, again 0 for Tx less than or equal to n, but v to the power Tx for x is greater than n. So the difference in between the deferred whole life and the PO endowment is the benefit is v to the power n for the PO endowment, which is n is a fixed point. But in here, Tx is a random point beyond n. We don't know the actual point. But in the PO endowment, we knew that the endpoint is n. But here the endpoint is Tx, which is greater than n, but we don't know the actual place. That means we can denote like the deferred probability, the actuarial present value of a continuous whole life insurance of a person who is at age X for n years is given like this. And since the insurance coverage starts from n, so it goes from n to infinity. And the present value is Vt, then we have to multiply it by Fxt. So Fxt is in here. And so you can use the integration to get this value. But if you can see it's like this. Uh, if you get a whole life insurance, the coverage starts from 0 and goes to infinity. So if you get a term life insurance, coverage goes from 0 to n. And if you get a deferred whole life, you get it from n to infinity. That means if you join the term life from 0 to n and a deferred whole life from n to infinity, you get a whole life. So that means without the integration, still you can say that the whole life net single premium is same as the summation of term life net single premium plus the deferred whole life net single premium. So this is another useful combination of net single premiums. And again, since we are dealing with VTX, so the second moment is taken by replacing delta with 2 delta, and it becomes, so this becomes, the notation says, this is the second moment of the present value random variable of this deferred whole life insurance. So this is for the level benefit. But if this if this is not level payment, so then it's easy to work with the integration because now the benefit is a function of t without having different level payments. We can directly integrate the function by after multiplying it by the density function to get the final answer. So that is how the deferred whole life insurance is defined. So now you can imagine the whole life, the deferred whole life, the term life, the PO endowment, and the endowment. Both are for the future lifetime, but sometimes we can combine two concepts together and define the whole life or define the endowment insurance. Now we can move to the next two cases. So, and then I'll summarize these 7 cases again uh, in order to summarize them in a table. So let's do it like this. I'll use this side. So up to this point, all these 5, whole life, term life, pure endowment, and the deferred whole life cases, we consider that the benefit was fixed and level. And if and also I mentioned that if the benefit is a step function, still we can replicate that uh, portfolio using a combination of level premiums. But suppose um, without having step functions, we can say the age or the benefit is proportional to the age. That means if that person, like starting from 25, uh, if that person dies at age 27.7 and 6 months, that means they have survived 2.5 years. So then your base benefit is 100,000. You multiply it by 2.5% and add it into the base. That means the benefit will be 102.5% at the uh, point of death. So in that case, we cannot discretely sum up things. So it's easy to uh, integrate using the fundamentals. So if I draw this, they are directly proportional. That means with the time, the benefit increases like this. So this is the benefit and this is the future lifetime. And if it is 1 to 1, then if this is H, then this is also H. So in that case, the benefit function is Tx, it's a random variable now, and the present value random variable is Tx times Tx. So the actuarial present value is T times Vt, the fx T. And if it is, so in here it is continuously increasing whole life. So since it is whole life, integral goes from 0 to infinity. If it is deferred whole life, then goes from n to infinity. So the notation says this is increasing. This is the actuarial present value, age, and also it says whole life because we don't have any kind of term indicators in here. And we have bar or continuous. So that is a precise notation which indicates different status. Continuously increasing actuarial present value of a whole life insurance purchased at age X. So that's how we can define this uh, notation. And the only difference between A bar X and IA bar X is that you multiply Vt by T and then multiply it by Fxt before taking the integration from 0 to infinity. So you can define it for decreasing as well. And also it's for annually increasing case as well. So for the annually increasing case, I mentioned, or I gave an example at the beginning. Um, so I'll indicate it as a function. So that means from 1 year it's 1. Then the second year it's increased. Third year it's increased. Like this, it's like a step function. And so it's being increased at every year, starting from 0. So now you can replicate this kind of an function using a set of level benefit payment. But still, since we have to work with the curtain random variable, we can think about this. So it's always when t is equal to 0, uh, then we add 1 and take the integer value. That means, uh, if you recall, this says integer part of tx. That is, if 0.9 bracket means 0, 2.1 bracket means 2. So in this case, you can see between 0 and 1, tx get the bracket for the bracket, it's 1. In between 0 and 1, that means tx plus 1 gives 1 for the bracket. Then 2, 3, and 4. That means if you replicate this kind of an uh, insurance product, it says you buy an insurance of 100,000 at age X. Then again buy another insurance of 100,000 at age X plus 1. Then X plus 2 and X plus 3. At every year, you buy the same product. So this is same as buying a product which doubles the benefit at each age or at annually. So then, since this is whole life again, the integration goes from 0 to n. But now you can see we don't have any bar for the I. That means this is increasing but not continuously. But the benefit is paid at the moment of death. So we use a bar only for the A. And then it is whole life. That's why we use X only. And the rest of the part is same. The additional part is t plus 1 bracket, which is the integer of t plus 1. And that is how we can define. So if it is decreasing, so then we can define it for a term life, because for the whole life we don't know, we cannot have the infinity minus something. But if we know that insurance goes only for n years, so then we can start from n, and at each year we can decrease the uh, benefit. So if this was, so this is increasing. Suppose this is a decreasing case for n year. So then n year decreasing means start from n. So after 1 year, it is n minus 1. So after 2 years, it's n minus 2. Like that, it goes for 1. So then you just need to replace this by n minus 1 and integrate it from 0 to n instead of infinity. So that's how we can define it. Even for this, it's n minus t integrating from 0 to n for the continuous case. The only difference is, so in that case, we use, so for this case, it's decreasing annually. So we don't have bar here, but benefit is paid at the moment of death and purchase age is X. So that's how we denote it. And this is equal to 0 to n minus t, and vt, pxt, mu x plus t, dt. So we can derive based on the information we have. So that is the entire uh, continuous cases we are considering for this chapter. And let's summarize it again from the beginning so that you can digest the concept easily. So I will start from the policy. Whole life, and Yeah, let's say notation of actuarial present value, and the actuarial present value for the expectation of the present value random variable, and the second movement of the present value random variable. So if it is whole life, that means starting from 0, the benefit is covered for the future. So at any point of the time, the benefit is paid. So the notation is continuously paid actuarial present value whole life starting at age X. And the value takes from 0 to infinity, and present value is Vt. Fxt means mu xt plus pxt dt. And the second movement denotes by this, or which it is denoted by this. So then you can use these two to get the variance, and to get the second movement, you just need to replace deltas as 2 delta in the actuarial present value case. And for the n-year term life case, from 0 to n, pay, but after that, we don't pay the benefit. And the notation says starting from X, the term goes for n years, continuously paid benefit, and only term benefit, which means benefit is paid between 0 and n. Then integration goes from 0 to n, Vt times pxt mu x plus t dt, and the second movement is x this. And for the n peer endowment, benefit is not paid in between 0 and n. The benefit is paid at this point and no benefit after that as well. The notation says there's no bar because there's only one payment time, but age is X and goes for n years. If survives at n, then pay one benefit. So the present value is Vn times probability of surviving for n. And this is given by this. Just replace this n in Vn by 2n. So now by combining the second and third cases, I can have n-year endowment insurance. Says from 0 to n, we have a payment of death benefit. At point of n, we have another payment for surviving, but after that, you don't have any payments. So we have continuous term life. And the formula takes you a summation of term life and pure endowment part. So the notation for the second movement says this, which means replace the deltas in the term life as 2 delta and replace the n in pure endowment as 2n. Then sum of those values, you get the second movement of the n-year endowment insurance. And for n-year deferred, whole life insurance, you get 0 to n and get nothing in between 0 and 1. But after that, you get a payment. So the notation says continuously, which means benefit is paid at the moment of death for a person who is at age X, but the insurance starts after n years. So this is integrating from n to infinity, Vt, Pxt, mu x plus t times dt. And this one is x deferred for n years. So this is same as removing the term life from the whole life. So now you can see these 5 different types of insurance are interchangeable, and most of them. So this one is given in the table. This one is given in the table. So for the continuous, so for the discrete case, and for the discrete case, you can find the discrete value and convert into the continuous case using the assumptions UDD, which will be discussed in future. So that is the practice we carry out in life insurance, and this is for the continuous case. And also we discussed about increasing insurance portfolios as well. So I could mention about the whole life. That means continuously increasing whole life. That means benefit is paid at the moment of death for a person who is at age X, and increasingly, so the increment is also linear and continuous. The formula says this goes from 0 to infinity and t times Vt because of the linearity, and the rest of the function is same as the level benefit. And annually increasing whole life benefit is paid at the moment of death, but increasing annually, so we don't have any bar here. So it goes integer part of t plus 1 times Vt, Pxt, ux plus t, dt. And also I mentioned about the increasing term life and the decreasing term life. So I'm not going to mention everything. Let's do it for two cases. So if it is increasing term life, you just replace infinity by n. So let's say decreasing in near term life. That means continuously decreasing. Benefit is paid at the moment of death. Start from X and goes to n years, and it is term life. So this is in between 0 and n. Maximum value is n. The last value is n minus t. So the rest is same. So decreasing annually, term life. There's no bar for D, but since it is benefit is paid at the moment of death and it is term life, so we are integrating this from 0 to n, but now n minus t, but for t, we get the integer part and multiply it by vt, pxt, mu x plus t, dt. So that is for the decreasing, but if it is, so we know that if it is increasing term life, we just replace n minus t by t and go from 0 to n. So here, again, for annual case, it's t plus 1 bracket from 0 to n for the term life annually increasing case. So those are the uh, cases that we can think about. But if you get something like this, so I mentioned that we can replicate or the same insurance portfolio, the product can be replaced by two or more different insurance types. So if you think about that in here for the increasing case, you can think like this. So let's say something like this. For the increasing endowment, so we knew that for the endowment, n-year term life plus the n-year PO endowment is there. So the endowment is the summation of these two. So for the increasing endowment, so this one has to be increasing because it is the randomly varying uh, benefit payment from 0 to n. But for the PO endowment, after n years, it's a fixed payment. That means we just need to multiply the Vn by n. So if it is continuous increasing n-year endowment, so it should say increasing continuously, death benefit is paid at the moment of death, starting from x to n, it says. And the increasing part is term life, which is death benefit is paid at the moment of death, and the benefit is also increased continuously, and after n years, it's just this. So this one is a one-time payment. So at that time, the benefit is n because they have survived for n years. So this is the special case. So you don't have a continuous case for this pure endowment part. So that was the point I wanted to mention. So this concludes all the different types of insurance we can think of under this chapter. And mostly we will be so you will be tested for whole life, term life, pure endowment, any endowment, and the deferred whole life case. So increasing case is for your knowledge. And now we can move on to the discrete life insurance part. Because if you know the concept for the continuous life insurance case, it's easy to adjust that concept to the discrete case. So in the continuous case, we integrated to take that expectation. The discrete case, we need to get the um, summation after multiplying it with the probability. So for the whole life, it's like this. So discrete means in terms of the payment. So in the previous case I mentioned continuous means the benefit is paid at the moment of death. So in this case, the benefit is paid after the death during the time interval they consider. If the time interval is annual, so then suppose like this. So then this person survives for n plus 1 years. Uh, let's say this is n and n plus 1 up to this point. So the death occurs in here. That means Tx. So the value of Kx is n because the integer value of it. The Tx is n point something. So the integer value of Tx is n. So the value of Kx at this point is x plus n. That means if the benefits are paid at the end of each year for a death occurs within that year, the benefit is being paid at this moment. And we need to take the present value of the benefit, take it to the present. So the person survives in blue up to this point and the death occurs in between n and n plus 1. If the death occurs in between n and n plus 1, the benefit is being paid at the end of that period, which is at the beginning of n plus 1. So the benefit is taken back from n plus 1 to 0. So that is the present value. So this is kx plus 1 and n plus 1. So this is kx times 1. So because this is the value of tx. And that means we need the deferred probability for this whole part. So we know that person survives up to n and the death occurs in between n and n plus 1. So that is the deferred probability of this. So this part is for a person who is at age x, survives for k years and death occurs within the next year. So that it can be represented by the multiplication like this or a difference of the two survival probabilities or the two death probabilities. We knew that. But the discount comes from k plus 1. So that's the important thing. So if this person dies in between 0 and 1, which is within the first year, that means the discount comes from 1 because the benefit is paid at the end of the first year. So we're almost sure that we take it back from 1 year. So that's the difference. So previously we multiplied by Vt, but here k plus 1 is the present value. So benefit is $1 now. And the notation says actuarial present value of a whole life insurance start at X, but it's not continuous, so we don't have any bars here. That is it. And to get the second movement, just replace delta by 2 delta and denote it by this. Says the second movement of the present value random variable of a whole life insurance where the benefit is paid at the end of the death year. And the variance can be taken using the same thing. You can see that the equation is almost similar to the continuous case where we only omit the bar above this capital A. And so this coverage period this for the whole life is uh, unconsiderable because we know that the insurer will pay the benefit at any time of the future lifetime. And but for the term life case, the coverage should be so the death should occur within the coverage period. That means the coverage goes from 0 to n and death occurs between 0 and n uh, is the situation. So that means the previous year before n is n minus 1. And here, the highest value we can get for the discount is n. That means the death should occur in between n minus and n. So the kx value is n minus 1 in this point and kx value is n at this point. So the death occurs in between these two. That is the maximum case. So if that occurs in here, the discount will come back from here. So the benefit is P. And so Tx gives you the occasion of death. So for this one is death. And in that case, we don't need to go from k0 equals 0 to infinity. So we just need to go from 0 to n. So since we cannot go beyond n, the maximum value for k is n minus 1. Because if the death occurs after n, we don't want to pay. So that means the benefit is 0. So we don't have to average that area. So the maximum value that k can take is n minus 1 because once this tx passes this n, it goes beyond the coverage period and the benefit becomes 0. So that's why the actuarial present value of a term life starting from x and goes for n years is given in this way without the bar, and the summation goes from k equals 0 to n minus 1. So you can see because v goes, so v to the power k plus 1 is the present value random variable. So if you substitute n minus 1 into k plus 1, so it will eventually give b to the power n. So that is the maximum or the distance we can go from 0. So that means that is the smallest uh, discount factor we can get because v to the power n is the uh, n is the largest value for the power, but 1 over 1 plus I is the discount factor. So it will become the smallest one in terms of the discount. So that is how it works. And the probabilities are same. So this is again the probability of death occur for a person who is at age X, deferred for the K years, and death occurs within the next year. And for the second movement, again, we replace delta with 2 delta, and we denote it like this: A, xn, and 2 is there, no bar, because it is annual. And variance is given in this term. So now you can see it's just the conversion from uh, continuous to the discrete scale. Now the benefit is being paid at the moment. Uh, it's not being paid at the moment of death. Instead of that, the benefit is being paid after the, so which means at the moment of the policy period, or the if it is annual, so the end of the year. If it is monthly, so then at the end of the death month. In that case, we know that how to compound, we found the compound interest rate. So then we have to calculate the compound V corresponding to that compound interest rate. So in the same way, for the level benefit endowment, so we know that the PO endowment part is just one-time payment. So it's still there. For the endowment insurance, so if the death occurs between 0 and N, there's a payment, and they survive, then there's a survival benefit at time of N. Since this is a one-time payment, we don't have any adjustment, but for this one, so we don't have any bar for A, capital A, and age is X, goes for N years. And for the term insurance, we don't have a bar, and we already didn't use a bar for the PO endowment term. So it's like this. So don't get confused with these ones. For the term insurance, we use 1 above X. For the PO endowment, we use 1 above N. So these are two different insurance types. And with the summation, you get the actuarial present value for the net single premium for this level benefit endowment insurance. So this is N year term. This is N year PO endowment. And to get the values corresponding to the second movement, just replace 2 delta, or delta with 2 delta. So you will get the present value. And finally, we are moving to the deferred whole life case. Still, the concept is same. Now, from 0 to N, we don't have any payment. So N plus 1 and so on. So if the death occurs at this point, then the benefits comes from N plus 1 to 0. If the death occurs in between N plus 11, then it comes from N plus 11 to 0. So that's how it works. So that means the summation should start from 0, not start from 0, it should start from N and goes to the infinity. And the notation says the actual present value from X to N, and after N years, the payment starts. No bar since it's the annual case or not continuous. And to get the second movement, just replace delta by 2 delta, and we denote it like this. And we can get the variance likewise. And if it is non-level, again, similar to the increasing case, the non-level benefit means a changing or varying benefit. and it's also a function of k. So previously it was t, now it's k, and we know that if it is continuously increasing, we multiply it by t. So in here, since it is discrete, if it is it is 1 to 1 and increasing, so then we multiply it by k plus 1. So our present value is v to the power k plus 1. That means, uh, for an example, suppose, let's say we remove this one, then this is increasing or annually increasing uh, all life insurance where the benefit is paid at the end of the policy year, and we multiply k plus 1 with v to the power k plus 1, and this is the deferred death probability from x to n, and death occurs x to k, and death occurs within the next year. So that is the same equation. We just introduced the term in brackets as a multiplicative factor for this one. So if this was deferred, then the summation goes from n to infinity, and this is k plus 1, and v k plus 1. This is px k and q x plus k. So that's the equation. And when it's come to the second movement, we replace delta by 2 delta and do the calculations accordingly. So that is the story of this uh, discrete random, or the variable, or which is called the quartet random variable. So I will quickly recall the equations there as well. So let's start from whole life. It says, starting from there, we have annual intervals, and the benefit is being paid at the end of that interval. So the present value says, actual present value of this annually benefit paid insurance, and formula is k is from 0 to infinity, and v is k to the power 1, and surviving from x to k years, and death occurs within the next year. So for the term life, if the death occurs between 0 and n, the benefit is there, and discrete benefit paid for n years from x, k goes from 0 to n minus 1, v k plus, and surviving from x to k, death occurs within the next year. And endowment goes from x to n, which is the term life. So in here it's term, and the term life plus, this is 1, and the pure endowment. And then we have n year deferred whole life, which is age starting at age x, but no payment for n years. That means k equal n goes to infinity, and v k plus n px k q x plus k. So that is the story for them. Let's quickly get one example for the increasing case. If this is annually increasing whole life, then increasing, and no bars since it is annually increasing, and also no bar for A because the benefit is paid at the end of the death year, and start from X. Since it is whole life, we don't have any other symbols. So this goes K equals 0 to infinity. And instead of T, now we are multiplying with K plus 1. The probability is same. If it is term life, infinity is replaced by n minus 1. So let's get a decreasing one annually, decreasing term life. So since it is term life, it starts from n. So decreasing annually, but death benefit is paid annually, starting from X, decrease for next n years. So K from 0 to n minus 1. And the maximum is n, and n minus k is there. And v to the power k plus 1. The probability is same. So that's how we can define this different insurance. So it's enough to work with this whole life, term life, endowment, and uh, deferred whole life. But this increasing and decreasing uh, insurance types are also discussed at this point as an additional source. But you will see, so now you should realize the similarities between these equations. The concept is there. So we start from 0. If we want this coverage start from the time of purchase, if we start from n, if we want to start it after n years, and we goes to infinity if the coverage is whole life, we goes to n years if the coverage is n year term life. And the PO endowment is just one time payment at the time of completion of n years with the policy. So that is the story. So let's do some calculations now to digest these concepts, and we will see it's easy to work with the concept once we figure out the equation. So we are given the following life table. Start from 90, it goes to 93, and you will see there's no survivors after the 92 years. That means at the age of 92, the number of survivors and the number of deaths are same for the same year. So the risk-free interest rate is 0.06, and we are asked to find the actuarial present value or the net single premium of a whole life insurance purchased by a person who is at age 90. Sorry. And the death benefit is paid at the end of the year of death. So because we don't have any bar, that means a 90 without bar and K always starts from 0. And we know the final year is 90. So we can grow from 93 is the maximum number we can get. And 90 is the gap. And we get, so N is this. So because we know at age 90, the Tx is 0. Uh, let's say directly get Kx. So this is 0, this is 1 at 91, this is 2 at 92, this is 3 at 93. And after that, so if the death occurs in here, K is equal 1. If the death occurs here, K equal 0, 1, 2, and 3. So for 94, it is undefined. So that means it goes from 0 to 3. So that is N. And since we start from 0, it goes to N minus 1. So 3 minus N. Since we have, that means we have only 3 terms to consider. and k plus 1 probability from 90 to k, and q goes from 90 to k plus 1. So we can have common equation for this one first, and this is 2 equals 0, and v k plus 1, and we know that for the deferred death probability, it is the number of deaths in between these years divided by the number of survivors at the beginning of this reference year. So number of survivors at age 90 is L90, and number of deaths in between these 2 years. That means if this is 2, so then surviving from 2 and death occurs in between 2 and 3. So we can get L 90 plus K minus L 90 plus K plus 1. Or that is D x to K. So we can get this entire thing as D, so 9 plus K. Because you know that if you divide or subtract 172, it's 28. Subtract 39 from 72, it's 33. Subtract 0 from 39, it's 39. So that's why it's this. And now, since there are 3 terms, that means divide this by this by this by this. So the probability are there. And the discount factor, since it is I is 0.06, so the discount factor is 1 over 1.06. And for k equal 1, k equals 0, it's 1. And the probability is L90 is 100 and D90 is 28. And for k equal 1, that means the discount factor is 1 over 1.06. And now k is 1, that means we need 2. And deaths at this age is 33 divided by 100. And for this one, discount factor is this, goes for 3 years, and deaths at this moment is 39 divided by 100. So then we can get the answer like this. And for part B, it's term life, starting from 90 and going for 1 year and term life. That means k equals 0 and n equal 1. So if we look at this, you can say for term life, if you could, so n equal 1, and this one goes from 0 to n minus 1. That means there's only one term where k equals 0. So the same thing, if I draw this, age is 90 and 1 year term is 91. If the death occurs between this year, the benefit will come from 91 back to here. So that's the same case. So V k plus 1 times Qx, the deferred probability, is same as 1 over 1.06. And for this one, again, L 90, because this is 90, and D 90. So we can have that one directly from there. So you can take that value in here. So I take the entire part, like 28 by 100, and divide by 1.06. And for C, it's 90. This is an endowment insurance. And we know that endowment is a collection of term life and PO endowment. Term life is taken from here, and for the PO endowment, it's like this. So the payment occurs in here, and the payment is $1. And you just need the survival probability. So that means surviving, if you survive there, the discount is 1 over 1.06. And the survival probability is 91. Same as 0.6. And surviving means L91 divided by L90, which is L91 divided by L90, and it is 72 divided by 100. So you can get this value and get the final value. So for the deferred life of 1 year, that means grow from N to the maximum value. The maximum value is here, 93 minus 90 minus 1, and the same term occurs in here. So we have only few terms there because this is 2. So we have two terms, k equal 1 and k equal 2. That is k from 1 to 2, vk plus 1. The death occurs in this year, and number of survivors at this point. So it's 0, 1. When k is equal 1, that means we need to discount it by k plus 1, so 2. And this one, again, 33 divided by 100. And for this one, 39 divided by 100. So you will get the answer for this one. And for part E, it is increasing starting from 90, and from the definition, k goes from 0. We have only 2 more years to go there, from 0 to 1, 1 to 2. And Since it is increasing annually, we multiply it by k plus 1, and the rest of the part is similar to the level case, which is D90 plus k and L90. So we get, for this one, it is 1 times 1 over 0.6 times 28 divided by 100. When it's k equal 1, this is 2 times 1 over 0.6 to the power 2 and 33 divided by 100. When it is 2, this is 3 and 1 over 3 and 39 divided by 100. So we can get the value for this one as well. So now you can see, so once we figure out the insurance type and the concept, then it's easy to build the actuarial present value equation. So once you build that, it's just recalling these probabilities from the previous chapter and how to apply those probabilities using the life table, and then just multiplying and get the summation of the term. So the concept, so in this chapter, we just need to identify the concept and figure out the correct equation. And then all the knowledge we gained from the previous chapter, which is the life table and the chapter 2, are applied in calculations after that. So we can do the final example for today. So in this case, we have some advanced. It says a special 3-year term life insurance, and C is the present value random variable, and the death benefits or so now we know that it's term life, so the death benefit is paid in between 0 and 1, 2, and 3. If the death occurs in between this window, we can expect a benefit payment. And the death probabilities given in here. So that means k is, when k is equal to 0, this qx is equal to 0.02, and when k is equal to 1, this one is 0.04. When k is equal to 0, 1, and 2, x plus 1, this becomes 3, so 0.06. So those are the death probabilities for these 3 intervals. And the following death benefits are payable. So now you can see the death benefits are 300,000, 350, and 400. So it's increasing by 50,000 at each age, and the expectation. So we can get it like this. So expected present value of the benefit payment, or the actual present value of this insurance, is, so if the death occurs in between 0 and 1, we expect 300,000. So that means the 300,000 is paid at the end of year 1 if the death occurs there. So we have to take it back to 0. So we divide it by 1.06. And the benefit, the present value is here. To have this present value, we need to have the probability. So this is 0.02. Because if the death occurs between 0 and 1, which is equal with the probability of QX1, we observe this present value. And now, if that person survives from 0 to 1 and death occurs between 1 and 2, then the benefit occurs in here and it comes back to here. So that benefit is 350,000 and it comes by 2 years back. So 1.6, 1.06 to the power 2. And for that, the person has to survive the first year. That means 1 minus 0.02 for the survival probability, and the death occurs with the 0.04 probability. And then, if that person survives the first year and the second year, and then the death occurs, the benefit is being paid at this point, and you have to take it back after 3 years. The benefit amount is 400,000. Since you are taking it back by 3 years, the discount factor is 400,000 divided by 1.06 to the power 3. And the survival probability from 0 to 1 is 0.98 and 1 to 2 is 0.96 and 2 to 3, the death occurs. So death probability is 0.06. So this is the corresponding present value. For this Z or the random variable of this benefit payment scheme. So now you can see at some point, so like for these special cases, we cannot use that equation directly for the level benefit payment. So the level benefit payment equations are useful when we are dealing with the standard life table. But in here, the special case, they have given the death probability and the benefit function as well. So that means we stick to the fundamentals and created this benefit scheme by considering each and every step. So first identify the benefit, then identify the time that benefit is being paid, then discount it back to 0. Since it is the expected present value, so we need the probability of having this event. So we have the probability multiplied by the present value. That is the contribution from that time. Then there's another possibility surviving from 1 year and the death occurs in the next year. So surviving from 0 to 1 and death occurs between 1 and 2, we can find the probability. If that event occurs, the death benefit is 350,000. Take it back by 2 years. So that is the present value and the corresponding probability multiplied by that. Then that is the contribution for the present value from there. The final case is if you have this like survive the first year and the second year, then the death occurs in the next year, then the benefit is being paid at the end of the third year, bring it back by 3 years. Such probabilities, survival probability for the first year, survival probability for the second year times the death probability for the third year. So since this is term life, you got this one. So if you simplify this one, it should be 36,829. And suppose I do another modification. For this term life, I add a PO endowment of 40,000. Or let's say it's 400,000 okay, of PO endowment. So that means the present value, actual present value of that one is 40,000 since it is paid at the end of third year. So this is the present value. And the probability of occurring this means surviving for the first year, surviving for the next year, and surviving during the last year. And this is the pure endowment. So if I create first modification, the second modification, if I create uh, endowment from term and pure endowment, then you just need to get this done. So this is the corresponding value for this uh, endowment insurance. And you will see the last two terms, the benefits are same. This is the death benefit. This is the this is death. This is endowment. And you can see the first three parts are same, just these two are different. So if you take this, when you get the summation for this one, you will see if you get these three terms as the common factor, the summation of these two is goes to 1. So that means if you have a pure endowment insurance, you just need to know whether that person has survived for the first n minus 1 years. Because during the last year, there's a definite payment at the end of the final year. So if the death occurs between that year, that payment will be the death benefit payment. If if that person survives that final year too, that payment will be the endowment payment. So it has to be either death benefit or the endowment benefit. So that means if that person survives up to the final year, then there will be a definite payment at the end of the final year. So you just need to get the survival probabilities up to the last year. So then you can multiply the present value of the final year and get it done. So that's the uh, point I wanted to mention in this case. So the question says only for a term life insurance, but I did two modifications by introducing a pure endowment, and after that, I combined that term with the pure endowment and created an endowment insurance. So those are the things that you can do to play with these concepts. So today we covered the continuous and the discrete life insurance concepts, whole life, the term life, pure endowment, and the deferred life. And also we did it for increasing and decreasing, but those are not directly testable. But I wanted to explain the concepts clearly. So then the next day, we can discuss about the monthly insurance or quarterly insurance, and then move to annuity payments. So that's the lecture for today. And